what we want to look at is the case of a ketone that's unsymmetrical. And I'm going to show this one. This is kind of classic. Okay, and I have data on it. It's always nice to have data. So here's cyclohexanone. To make it unsymmetrical, I'm going to add a methyl group here. So if you look at one side of the carbonyl, I have a methine carbon with a methyl group. And on this side of the carbon, I have two protons. So I'm specifically going to draw these two types of protons in different colors. So here I have a methylene. Okay, so this is really a secondary type of hydrogen system here. Whereas on this side, I have a proton on a tertiary carbon. So this is a tertiary hydrogen. Okay. Now, because I have two different types of hydrogens here, I can basically remove those protons differently. And so here, we're going to look at loss of the the secondary hydrogen. Okay, so if I lose one of these hydrogens on the left here, the enolate that I form looks like this. Okay, and one of the things I haven't been doing is, up to this point, I haven't emphasized that these enolates are resonance stabilized. So let me push my arrows, and again, I have this form of the enolate. Let me put all my electrons. Okay. Now I'm going to lower this a little bit. I'll just see. I just want to ask the question. So here I have an enolate, right? And this enolate has two resonance forms. Which form is more important and why? If anyone can answer that question. Do you expect the resonance form to be the better resonance hybrid to be the form on the left or the one on the right?
The one on the right.
Okay. Anyone else?
The one on the right.
Okay. Anyone else?
Because it shows that oxygen has a nucleophile.
Yes. Okay, so the answer is, you guys are all correct. It's the one on the right. So this is a better resonance hybrid, right? The reason for this is specifically that recognize that here I have a carbon that has a negative charge, whereas over here I have an oxygen with a negative charge. And one of the things you should have learned in the acid-base chapter is that across a periodic table trend, atoms tend to want to hold a negative charge more effectively because it's electronegative. So the more electronegative element always prefers the negative charge. So since carbon is less electronegative than oxygen, this is the better resonance structure. Okay. So again, I just want you to see that because sometimes I shorthand, I only show this form, but in reality, this is the better form of the resonance hybrid.
Also, with the methyl group on there, the hydrogen attached to that methyl group can help stabilize the oxygen as well.
Oops. I'm sorry. I'm playing with different colors here. This should be fine. No, there's no effect with that. That's not really affecting the resonance hybrid, having that methyl group. Okay. So let's now consider, what if we lose the proton? So here it was, I showed the loss of the methylene protons. How about if I lose that methine proton? The loss of the tertiary hydrogen. If I do this now, I get this enolate. And again, I'm going to show the resonance form of this. So I'm going to push my arrow here and here. And now I have the enolate where the negative charge is on the oxygen. Okay? All right. So,
can you put it up a little, please?
sure. Let me put this up. Back up a little bit higher. Can you guys see that okay? Yes?
Yeah.
All
That's
right.
fine.
So basically here we have the difference of what we call thermodynamic versus kinetic enolates. Now, let me just give you guys a couple of things. Thermodynamic they're favored by using a weak base. And so here I'm going to put in parentheses, what are those weak bases? Often we use sodium hydroxide or sodium ethoxide. Most of the alkoxide salts are weak bases. Thermodynamic enolates formed by using a weak base, and IE establishes an equilibrium. Okay. So again, remind yourself of the top part of the slide. This is what I showed here. Sodium hydroxide, when it attacks ketones in general, I have this equilibrium where the equilibrium is not towards the enolate, but towards the ketone. So if I'm looking at thermodynamic enolate, and if I'm using one of these hydroxides, recognize I should have an equilibrium. That's what I just shared with you. Okay. Now, on the other hand, kinetic enolates in general are formed fastest. Okay? And so one of the things we find is, and just like whenever you say kinetics, you often say, when we think about kinetics, is something going faster. So kinetic enolates are formed fastest, and usually this means that we are using aldehyde as our base. So I'm going to say aldehyde favors this one. Okay. And so let me go back here then, let's try to explain this then. If I lose the blue protons here, right, I form this enolate here. And this enolate, I'm going to focus on this hybrid here. And I'm also going to focus on this hybrid and compare. Okay? If you consider double bonds, right, this enolate looks like a double bond, except it has an oxygen. Okay? One of the things you should have learned about double bonds in the alkene chapter in 228 is that if I have double bonds that are more substituted are more stable. So notice that here I have a double bond that has a methyl group, as opposed to over here I have a double bond that has a hydrogen. So consequently, this is more substituted. So we should stay more stable. Okay? So if this is more stable, this should be the thermodynamic enolate. Okay? So this is the thermodynamic enolate. On the other hand, the kinetic enolates form fastest. Well, if you consider that aldehyde, we talked about it, is bulky, right? It's sterically hindered. because of these isopropyl groups, it's not going to react as fast with this methine hydrogen because I have this big old methyl group, right? This methyl group has a carbon. I'm not going to show all the separate hydrogens, but it has all the hydrogens, and that van der Waals radius is going to block that hydrogen here, make it a little bit more sterically encumbered than this methylene here, which is only competing for one of, well, we have two things here. One is, this proton here is adjacent to another proton, whereas this proton is adjacent to a methyl. So this is less sterically encumbered. And you could also think about statistics. I have a chance to get one of two, whereas over here, I only have one. So kinetically, this is a faster site. So we say this is kinetically faster. Okay. So what I want you guys to be aware of and to apply here is just recognize that when I have an unsymmetrical ketone here, if I remove the proton on the more substituted side, that leads to the thermodynamic enolate, okay? And in order to favor that, you want to use a weak base. On the other hand, if you want to form the kinetic enolate, the enolate that's formed by abstracting the protons that's on the least substituted carbon, you want to use a very strong base such as aldehyde. Okay, so let me just share with you how one could apply this. Let's consider a reaction, and let me give you some data to showcase this. Okay, so let's look at that methyl ketone. If I treat that methyl ketone with aldehyde first, and remind yourselves that aldehyde, because it's strong, it's going to form 100% of the enolate. It turns out that of these two enolates, specifically at 0 degrees, this is formed 99%. I only get 1% of the thermodynamic enolate. So I'm going to look at this guy here, and now if I treat this with methyl iodide, and actually, let's do this. The product I get from this reaction okay? So again, what I want you guys to see here, and again, we'll revisit this in chapter 23, but specifically, I want you guys to recognize that aldehyde, if it's unsymmetrical, often abstracts a proton that's less sterically hindered. So
Hey, Professor.
Yeah.
Your screen's still frozen for a lot of us. Like, this method's freezing like everything.
What's freezing?
Like screen, like I can't see the product of your notes. Like it's just
The
frozen.
document camera.
Document camera? Oh. Sorry. Can you see that?
I
No,
can't.
it's still frozen.
Yeah, it's still frozen for me too.
Okay, let me stop sharing, and let me share it again. Can you guys see it now?
Yes.
Yeah.
Okay, sorry about that. I don't know why it froze. So what I was getting at, again, how long ago has it been frozen? Last couple minutes? 2
10
minutes?
seconds.
Yeah.
While you were writing.
This last part? This last part here?
The CHI part, it froze it there.
Okay. So what I was saying is, let's look at methyl ketone here with the aldehyde at 0 degrees. Okay. What the data tells us is that 99% of the enolate is the kinetic enolate, the enolate in which I abstracted the protons on the least hindered side. Okay. Do I have any formation of the enolate that's thermodynamic form from this? Yes. I'm not showing it, but it's only 1%. Okay. So I'm only getting 1% of that enolate. 99% is the kinetic enolate here. So now if I treat this enolate with methyl iodide, my point is the methyl group goes on this carbon, and I form very little of the product. Let me just show that would exist if I formed the thermodynamic enolate. Okay. And let me emphasize that's a methyl for methyl iodide. Okay. Again, I'll make certain I try to upload these slides later on today for you. Okay. All right. So one final thing before we get into some of the new stuff. I want you guys to start thinking about this and seeing where we're going to go. Okay. So